3.5 notes are about local linearization. So if you have a curve, looks like that, say that's f of x, you can find your point there and make a tangent line. At the point of tangency, at that point I just drew, at the point of tangency, f of x, which is the curve, and the tangent line have the same value. If we kind of zoom in, so to speak, on that tangent line, even though my curve looks different, ignore that, we can actually extend that tangent line, because for a small local area, they are close, meaning the value of the function and the value of the y value of the tangent line are pretty close to each other. We can replace or substitute the tangent line for the function near or at the point of tangency. Here's how that works. For example, we can use local linearization. It's a nice, multi-syllabled, seemingly made-up word, to approximate square root of 10. So this is the function. So we're taking the square root of something. So the function is y equals square root of x. That looks like this. So we're going to find the slope of a tangent line and find the equation of it, and then estimate right around it. So we don't know square root of 10. We're going to use the point 9, 3, because 9 is near 10, and we know what the square root of 9 is. So if you're like, oh, 11 is pretty close to 10, it is, but what's the square root of 11? It's not anything nice. So we'll use the point 9, 3, and we are going to write the equation of the tangent line at that point 9, 3. So since y equals square root of x, or x to the 1/2, y prime is 1/2 x to the negative 1/2, which is the same as 1/2 square root of x. Since that's true, then y prime of 9, since that's our point we're using, is 1/2 times the square root of 9, which is 1/2 times 3, which is 1/6. So then we have our point, we have our slope, and now we can write the equation of our tangent line. So y minus 3 equals 1/6 x minus 9. So there's our tangent line. Again, let's say it's up here where we looked last time, let's say this is the line we're looking at. I'll make it a color we can actually kind of see. That's a little better. Let's say that's our line. We're going to estimate right around it, and now is where we go back to, oh yeah, we were approximating square root of 10. So now we have y minus 3 equals 1/6, and now the x value we're using in this line is 10. So we just replace 10 with x. So y minus 3 equals 1/6 times 1. So y minus 3 is 1/6. We add 3. Y is 3 1/6. So essentially what this tells us is that the square root of 10 is approximately 3 1/6. So that would be our answer. Okay? And just for comparison's sake, the actual value for square root of 10 is 3.162. So we're pretty close. Now for another example. F of x equals negative 3x squared plus 4x plus 2. And we're going to use local linearization to estimate, same as find the approximation, to estimate f of 1.2. And then we're asked to find, is your approximation an overestimate or an underestimate? So we'll deal with that second piece later. But to start with, we're trying to estimate f of 1.2. So we're going to use x equals 1 because 1's pretty close to 1.2, and I can fairly easily find f of 1. So f of 1 is actually negative 3 plus 4, which is 1, plus 2, which is 3. So our point is 1, 3. Then we find our derivative, which is negative 6x plus 4. And then we find the derivative at 1, which is negative 6 plus 4, which is negative 2. So in the equation of our tangent line is y minus 3 equals negative 2, which is our slope, times x minus 1. So now we're going to find our f of 1.2. So y minus 3 equals negative 2 times 1.2 minus 1. Y minus 3 equals negative 2 times 0.2. Y minus 3 equals negative 0.4. If you add 3 on both sides, you get y equals 2.6. And the way we will write this is f of 1.2 is approximately 2.6, because it's not exactly 2.6, because the whole thing we were doing here was finding an approximation. That's the point. So as far as the overestimate or underestimate, I know that this function is a quadratic, and the leading term is negative, so it's going to look like that. And so anywhere you draw a tangent line, if you estimate values using that, anywhere you look, let's say here's our actual y value. That would be our tangent line y value. So no matter what, again, bad picture notwithstanding, your actual y value is going to be less than what your tangent line tells you. So this is an overestimate.